Good morning. I think we are waiting for some more people, right?
Yes, Swati.
Okay. So let me know when everybody is in.
Swati, I can start.
Okay. So one thing is that I have been asking for class 6 state board syllabus for a long time. Syllabus, not syllabus, but the textbook crunch.
I uploaded in the drive.
You need to send me a link.
Okay, I will send you the link. I uploaded.
Okay.
Right. Okay.
Okay. Uh, so, and I also realized in the task setting, there is one mistake that I made, but that's okay. So we can look into that. So one of the things, the first question was this, the pattern between among the grid of 2, 5 and 7. So, and many of you correctly identified that these are where the lines are vertical. Okay. It would be good if you can have the grids in front of you. Let me see if I can project that. Yeah, so if you look at the first the top, you can see vertical lines. For these three, we get vertical lines. Share screen again. Okay. So the question is, why do we have vertical lines for 2, 5, and 10?
Swati, please repeat the question. We can't hear your voice.
Why do we get vertical lines for 2, 5, and 10? Not for any other number.
Because the factors are in the vertical line only.
Factors of what?
Factors of, for example, factors of 10 in the vertical column.
Right. Now, why is the 10 becoming important here?
Because the intersection of the 2 and 5 is 10. So
Not that. The thing is, each row has 10 numbers. We are starting a new row after 10. That is where the 10 is very important. Okay. So instead of this, if for example, we had taken now, for example, these vertical lines. This is a grid for which number? Multiples of which number?
3.
Right. Now, in this case, you got vertical lines for 3. Why do you think that happened?
Because the total column is 9.
And
It's a factor of 3.
correct. Similarly, if we have Just bear with me for a little while. Bad idea. Okay. Now, if you look at this grid, then what do you see?
The first one factor of 3, the second one factor of 4.
Factor of 4. There are dotted 12 columns, so it is divisible by 3 and 4.
Exactly. So the number of columns, okay, so if you have the number of columns. Now any factor of the number of columns will appear as vertical lines. Okay, so that is one very interesting aspect. Okay, and you can do a lot of pattern type of activities related to this. You can give just the grid, the color pattern, and you can ask children to figure out what is the what for which number it is there. The next one, which is also important, is now when you see this, you see some diagonal lines, right? Now, what is special about these diagonal lines? Okay, before that, one thing, when we put things like this, okay, this vertical column thing, when we do it with groups, 10 columns, then what happens is that naturally every column has the same units digit, okay, and every row will have kind of a different tens digit, mostly except the last one. Okay, so then when you look at these vertical lines, you can relate it to that. You can relate it to the units digit immediately. So the divisibility rule can be derived from here. Okay, now what about these two, for where you have a diagonal line? What is happening here? When you go from along any of these diagonals, when you go along any of these diagonals, what exactly happens? So let's say you go from, let's take 58. You go from 58 to 67. What exactly is happening?
It's increasing by 9.
Correct. Now, in terms of the digits, an increase by 9 is the same as an increase by 10 and a reduction by 1. So if you look carefully, the tens digit increases by 1 and the units digit reduces by 1.
Yes, sir.
Right? So what happens is the digit sum remains the same. Can you see that?
I don't understand.
The digit sum, the sum of the two digits,
Okay, okay.
that remains same because the tens digit gets increased by 1 and the
Yeah,
units digit gets decreased, reduced by 1.
yes, yes.
Okay, so the total remains the same. Now, in some cases, you may have to do a repeated digit sum. So, for example, when you go from 60 to 69, here the digit sum is 6. But if when you go to 69, the digit sum becomes 15. But then again, when you add them, 1 and 5, you get back to 6. So in some cases, I think in case of this last two, you have to do kind of a repeated thing, but otherwise it's simple digit sum. Now notice that the digit sum along any of these columns is basically, decided by whatever is this number. So this digit, the digit sum is 2 for 211, that column. It is 3. Then throughout it is 4, 5, 6, 7, 8, all the way up to 10. And then it again becomes 2, 3, 4, like that. So it kind of goes along that pattern. And in fact, if you look at these diagonals, you will see there is a recurring pattern of 3, 6, 9, then again 3, 6, 9. And if you continue this grid vertically down, you'll see this cycle repeating 3, 6, 9, 3, 6, 9, 3, 6, 9, like that. You can also get it from the table of 3. Okay, if you do digit sum, you will see that that's what happens. And you can clearly see that in case of 9, it's just those. So it's a subset of those of 3. Okay. So this is something that comes out quite nicely and you can immediately link it to the digit sum. There is another way which you can think about this. So whenever we have a number and we are looking into divisibility rule, the basic idea is, let's start with the number n, okay? And we want to check if n is divisible by, let's say, m. So what we do is we write n in terms of two numbers, m plus small n, where the small n is a relatively much smaller number. Okay. So when we have, when m, the small n is 2, 5, or 10, the way we split this is we write it in terms of 10 a plus n, where n is the units digit. Okay. And then if n is divisible by 2, 5, or 10, then, okay, so here is one more thing that needs to be added. So we need n to be a relatively smaller number so that it's easy to check. And we need that this n is clearly divisible by m. Okay. Write it in this of the form, let's say some a times m. Okay, so that kind of takes care of it. So you can see that it's in that form. It's of the form. Okay. So all we need to do is look at the units digit, and if that is divisible by, then n is also divisible by okay. Now if m is 3 or 9, then what happens is, let's take an n. So you can think of n as, take an example. Okay, before that, let's talk a little bit about 4. So if m is 4, then you notice that 4 divides 100. So then you want to write n as 100k plus n, where n is the 2-digit number made with the tens and the units digit. Okay, so if n is 3572, then n, small n, will be 72. Okay, and so clearly n is 35 3500 plus 72, and we realize that 3500 is 35 times 25 times 4. So all we need to do is to check for 72. If 72 turns out to be divisible by 4, then the whole thing is divisible by 4, because this part is already divisible by 4. Okay. If we have m equal to 8, then 8 divides 1000, and so we will like to split it as, 1000 k plus n. So n will have the hundreds, tens, and units digits. Okay, so for n equal to, so you can think of, let's say, 2, 4, 6, 7, 5, 8, and you want to write it as 2, 4, 6, 0, 0, 0, which plus 7, 5, 8. Now 2, 4, 6 times 1, 2, 5 times 8. So this part is clearly divisible by 8, and so you now need to check only for 7, 5, 8. Okay. However, once you know something is divisible by 2, you can, use that to figure out, you can divide that number by 2, then the number obviously reduces, then you can again check if it has another factor of 2, etc. So divisibility rule of 2 is more important than 4 and 8. You can live without 4 and 8, but 2 is very, very crucial. Now, I better change the screen. Okay. Now, when it comes to 3 and 9, so now let's look at that case. Let's take n equal to okay. Now you can think of this as 4 times 10,000 plus 6 times 1,000 plus 7 times 100 plus 3 times 10 plus 1. Now this can be written as in this form. And then you can have, you can split it. So you collect all the multiples of 9s together. So that gives you the first number. And then you have the next one, which is essentially the digit sum. Okay. So this is clearly 9 times something. and this is the digit sum. So all you need to do is check the digit sum. So let's see how much is the digit sum. It turns out to be 21. Okay. Now compared to this number, which is a 5-digit number, this is a very, very small number. And that is where the efficiency lies. Okay. So the difference between the rules of 3 and 9 is that this number needs to be divisible by, if it is divisible by 3, then the whole thing is divisible by 3. If this is divisible by 9, then the whole thing is divisible by 9. So this part remains the same. Okay. Only here is the little difference. So 3 and 9 can be explained very nicely here, and you basically have a recipe to get that big number and then whatever is left out. Okay, so there is a very nice way of splitting the two. When it comes to 11, then it is kind of similar. In case of 11, see, for 11, the pattern doesn't emerge out only with this grid, because this grid doesn't go that far. Okay, and that is why I asked you to read that article, because there we explored it and how it emerges out of that. Okay. Did people read that article?
That link that doesn't work, Swati. That's a wrong link, I think.
Okay, then shouldn't you have told me about it? Okay, let's see. I see why that link may not have worked. Okay, hang on. Okay, they changed stuff, and that is probably the reason. Okay, just hold on a second. I'll show you the article right now, and I'm going to send you the correct link. The website had got hacked, and that is why that link, so it hasn't been updated yet. Okay. So this is the first grid that you are familiar with. Now, if you extend it, and then if you collect all the multiples of 11 and you put them in a grid, you notice that in this part, wherever it is white, the alternate digit sum is the same. This is the first case. In the 209 is the first case where the alternate digit difference. What should I say? Okay, that's where the full form of DADs come in. I'm trying to see if we mention it here. No, later we mention it. The full form of DADs, let me say it out here. It has nothing to do with daddy. Difference between alternate digit sums. Okay, that's what the whole full form of DADS is. Difference between alternate digit sums. Okay, so to get that, you have to actually go all the way up to 209, and that's when you first time get that the difference is 11. Okay, and then if you go further, then this is the first time, 4070 is the first time when the difference turns out to be negative 11. Okay, so you have to play with quite a bit of patterns to see, how this works out. But and then you need to kind of tweak the table a bit to get, here you can see that you can see it kind of bends over. It's not together. But the moment you change the grid slightly.
Share the screen.
Oh, sorry. Yeah. So see here, the pink is kind of, split across the border, right? In two parts. You can see that it's kind of, in two parts. So when you tweak the table a little bit, okay, so here we had 1, 2, 3, 4, 5, 6, we had 10 columns. Okay. From that, if we tweak it to have 9 columns, then suddenly we have the, the pinks and the blues together. So it's quite fascinating. And there are some other patterns that come out. Okay. But what is important is how does it work? Okay. So there are two ways of looking at this. So one way will be, if I don't go through a pure algebraic part, okay, so now we are talking about m equal to 11. So the important thing here is to note that you can think of 11 as 10 plus 1, and on the other hand, 100 minus 1, 99 is clearly divisible by 11. Now, if you look at so let me put it this way. 10 plus 1 equals 11. Okay. So now let's take this number now this is nothing but 11 times 91 or 91 times 11, again divisible by 11, whereas this next guy 10,000 minus 1 is 9999, which is clearly 909 times 11. Okay. And you can keep going. So if you have 5 zeros plus 1, that will give you this, and you can figure out that this will be, I don't know, 999, something like this. Okay. And so you can see how for the odd powers of 10, if you add 1, you are getting a multiple of 11. Sorry. And for the even powers of 10, if you subtract 1, you are getting a multiple of 11. So now there is some algebra behind this. If you have 10 raised to an odd power plus 1, then you can factorize this as 10 plus 1 times something. Okay, so which is 11 times something. Okay, this can be factorized like that. Whereas if you have 10 hat raised to 2k, then you can think of this as 10 raised to 2 raised to k. Okay, and 10 square hang on, minus 1. Yeah. Okay, you can think of it as this. Okay, so it will have a factor of 10 square minus 1 and then something something, and this is basically, okay, you can even split it further. It is 10 plus 1 times 10 minus 1. Application of a square minus b square. So we end up getting 11 times. Okay, so for the odd powers of 10 we need to add 1, and for the even powers of 10 we need to subtract 1. So let's look at an example and see how this will work. So let's take n equal to, let's say, 3, 5, 8, 6, 4. So this is 3 times 10,000 plus 5 times 1,000 plus 8 times 100 plus 6 times 10 plus 4. So now we need to make the first part all multiples of 10. So now let's see, 3 times So this is an even power. So we add one more to it. Okay, plus 5. So this we write as no. This one we write as, and this one we write as okay, 8. Okay, and we're almost there. So we take, this is clearly let me just collect this. We'll get the 3, then minus 5 plus 8 minus 6 plus 4. So this is clearly, 3 times 909 times 11 plus 5 times, I think, 91 times 11 plus 8 times 9 times 11 plus 6 times 11. So that part is clear. And here we have 3 plus 8 plus 4, which is, if you take the alternate digits, the sum of those, minus 5 plus 6, again, the other alternate digits. So this together gives us 11 times something plus, this is the digit sum of units, hundreds, 10,000, minus digit sum of tens, thousands. Okay, so this is the alternate digit sum. This is an alternate digit sum, this is another alternate digit sum, and then there is the difference between the alternate digit sums. Okay, so this rule is relatively more complex, but it's a very efficient rule because you see, you look at this number, this is very, very small, very, very small compared to a 5-digit number. So that's why this is quite efficient compared to the rule of 7. Now, all these rules we have discussed are, have efficient rules. Now, if you look at the pattern, see, these are the numbers which have simple patterns. Straight vertical lines or diagonals. And we have rules for them. anything else okay, this is for 4, then 6, 8 and 7. They don't have such a neat pattern, but then 4, 6 and 8 are not prime numbers. Okay, so there is a way out. Okay, they are not so crucial. However, 7 is a prime number, and so there is no easy way. Okay, so that's a problem. Okay, now one thing which is important is that there is a difference between how the grids of when you have 2, 5, 10, those grids have some commonality. Okay, intersection of 2 and 5 gives you is intersection of grids of 2 and 5 is the grid for 10. Okay, that's very clear. Similar thing you will get for 2, 3, 6. But for 2, 4, 8, is that the same thing? I mean, think about it. Okay. Let me put the grids next to each other so that it's very clear. That's 2, then 4, okay. Now, can you see that? I mean, if you take the intersection of these two, what do you get?
We got 4 only.
Exactly, you do not get 8. And why is that the case?
Because 4 has already in a factor of 2.
Exactly. See, when we are talking about two are co-prime, so these two grids do not overlap exactly. One is not set of the other. Same if you have 2 and 4, there, I mean, the grid of 4 is a subset of grid of 2. So in this case, it's a different situation. Okay. So similarly, to get grid of 15, you use grids of 3 and 5. So to get grid of 12, which ones you use? So I gave you two choices, 3, 4 and 2, 6.
3, 4.
3, 4.
Yeah. So you use 3, 4. Okay, and you can again see that. This is the grid of 6. Okay, and you can see it is already, within the grid of 2. So if you take this and grid of 2, then that's the thing. Now, so a lot of activities can be designed around this, and you can get children to figure out what exactly is happening, um, what are they doing, what are their discoveries, what insights are they getting. You can actually design even worksheets also. Another thing, if you can make, that would be good, you make one simple number grid. Okay, so you just make this grid. So you have to do this on cardboard or something thick. Okay, so you make this grid, and then what you do, so with the numbers. Okay, so it should be at least, I would say, at least, let's say, at least a foot long, at least 15-20 centimeters big, 15-20 centimeters by 15-20 centimeters, that big. You make this, and then you make
Yeah, are you
similar
sharing?
ones. Hello?
So please share.
I don't have the physical thing on me because right now we are in a transient phase and I don't have access to the actual boards.
Okay.
Okay, so this I will be simply, hang on. So what I'm saying is you make this. Okay, you make a board which has this, all the numbers in this form, and then you make a similar board but you put in holes there. So let me just show you how the next one will look like. Hang on, just bear with me. Okay. This is how the next one is going to look like. Whatever I am, highlighting, that should be cut out. Okay, maybe you remove this part. Okay, so the pink parts are what you remove, and if you superimpose this on that, only the the multiples of 2 will show. And similarly, you can make similar grids for so this will be the grid for 10. Okay, and similarly you can make grid for uh, each of these numbers. So ideally you want to make grid for these six. Okay, definitely the first 5. Even if you don't do 11, the other things you should. Okay, so making this, especially making these two, takes time. It's not so easy because here you can cut out big rectangles. Here you have to cut out individual squares. So this is going to be, time consuming. But if you do that, and then it is a lot more fun and good exploration when you superimpose these on it. Okay, and you can see only the multiples of a particular number visible through the grid. Okay, so if you can do that, that will be good. Sometime in October, I will be able to show you the exact boards to give you better idea. Not right now. Okay, so that's something I wanted to mention. Now then, the next part of the task had to do with prime factorization and number of factors. And from whatever I have seen, that you have got the basic idea. I'm going to share something with you, and that will illustrate it even further. Next, I had some questions on HCF LCM. And one question was that, okay, why don't we have LCF and why don't we have HCM? Okay, so this is lowest common factor. Why don't we talk about lowest common factor? We talk about the highest common factor. Why don't we talk about the lowest common factor? Yeah, come again.
The lowest common factor for all the numbers is 1.
Exactly. See, this is very boring situation. There is nothing, different. It is always 1. Even before you tell a number, we know it is 1. It's a very, very boring situation. So that is why it doesn't deserve to have a new name. Okay. But what about this guy? What about highest common multiple?
It keep on going. It's
Yes. There is no highest. There is no upper bound. So this is not possible. Okay. Now, few things that needs to be mentioned is when you have factors, right? And the factors are all less than the common factor. Okay, no, let me say the common factors are all less than the HCF. Or in other words, you can say HCF is multiple of any common factor. Okay. Similarly, it's the reverse case with common multiples. Okay. Any common multiple is greater than the LCM. And in fact, LCM is the factor of any common multiple. Okay. So, for example, if you take, let's say 4 and so the the multiples of 4 will be 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, okay. So these are the multiples of 4. Now look at 10. So the multiples of 10 are 10, 20, 30, 40, 50, 60, 70, etc. Now among these, okay, is there any way I can highlight something? I doubt it. Okay, I can make some things bold. Okay. Okay. Nope. Okay. No, that will not work. So you see, what is common between both? If we have this, now the common things, common multiples, the CM are going to be 20, 40, 60, etc. Right? And you notice, so then LCM is 20, and you notice that all the common multiples, they are basically multiples of the LCM. So if you get LCM, you can generate all the other multiples, all the other common multiples. Okay, so this is very important. Similarly, if you have HCF, you get all the other common factors. They will be all factors of it. Okay, so this part is very, very important. Now, yeah. Okay. Now, then I had asked you to find out why do we need to learn LCM? So any thoughts on that? I believe we have discussed this.
It is for fraction addition.
So now the question is, so then I had asked you to find the LCM of two given numbers. And again, I think you got that, it's very difficult to do that with prime factorization. It's possible to do that with HCF. You can find that. And once you find HCF, then that can be used to find LCM. Okay. Did anybody try the other link that I sent on HCF LCM?
Yes, sir.
So did it make sense? Did you get what?
Yeah, so you sent that link. That link is not working. So I got it. I get rid of that and I searched in internet. I got another link. So I got that.
No, I sent you two links. I can understand that the at right angle link was not working. The other link was also not working.
No, that link is working actually. This link, that learner.org is not working. What is that area?
Right, that one was not working. Okay, that's strange. Okay, so if that link doesn't work, oh, I see, page not found, huh? Okay, that's sad. Okay. Okay. New learner, okay. So did you find the alternative link?
Yes, sir. I will share it.
Yeah, please share. Yeah, because then I want others to look at it. So maybe next time we can start with that. Okay. So let's see. Yeah, I need to send you. So, but the at right angle links worked. Did the at right angles link work?
Which Which one? Sorry, the first one, dads or something.
Yeah, yeah.
Yeah, it's working.
Okay, okay, so great. Okay, good. So, okay, got it. So you guys are going to send the updated link for LCM HCF, and we will discuss that maybe a little bit next time. And I'm going to share with you a write-up. Now, let me ask you very quickly, did anybody try finding the LCM of those three numbers, all three numbers?
Yes, sir.
Okay. So if you did, try to be a bit more adventurous and see if you can find the common rule. Okay. So if you want to find the LCM of any two numbers, see, the formula for two numbers is kind of like this. LCM is LCM times HCF is equal to, m times n, if m and n are the numbers. So if you can find, if you are given two numbers, you can definitely find the HCF, and then using that you can find the LCM. Okay. So it's not a very complicated formula. However, if there are three numbers, then what will be the formula? Okay, so if you feel brave enough, try to figure that out. Okay, and don't cheat and look at what I'm going to send you. Okay. Any thoughts, any questions?
I have a question on that area model. But,
Yes,
yeah,
please go ahead.
Yeah. No, but we will discuss. You said we will discuss next.
No, but still pose your question.
No, I don't understand that second part.
What is the second part?
Actually, they have taken. They have explained about HCF.
Right.
And they moved into LCM part. Then that,
Right.
yeah.
Okay. Okay, so we can definitely discuss that next time.
Yes.
The thing is, if you have certain manipulatives, if you make certain manipulatives, it is possible to do that as an activity, or without the technology, without going to that website. For the HCF part, all you need is dot sheets. Okay. But for the LCM part, you need to make some cards. Shiksha Mitra makes it so you can buy from them, or you can make it yourself. Okay. And then, you get to play with them and figure out what happens. So share the link and we will discuss that next time.
Yes, sir.
And I personally feel there is an advantage to doing it on the dot sheet or with, different cards, rather than on that website. At least the version of website I had seen earlier. And so if so the technology kind of gives something away too quickly. Okay, so that's not necessarily a good idea. Anybody else has any other questions? Anything? Okay, then that's all we have for today, and I'll see you on Monday.
So I have shared that link in the chat.
Yeah. Got the link.
Okay.
Thank you. It talks about models for multiple. Okay. Okay, I'll take a look at it. Okay. Okay. Yeah. Yep, it is there. I see. They have removed the interactive part. The interactive interface they have removed, it looks like.
So do you mean the divisibility rule? No, yeah. Hello. Let's Swati. Hello. Is it all? We will stop the meeting. Hello.
Hello?
Yeah, okay.
Yeah, we can stop. We can stop.
Yeah.
Okay. Thank you.
Thank you.